Hello everyone, I'm Dusan Mafrur. I'm one of the tutor of database principle course, and today in this video lab practical we are going to study about the tree, especially the complexity of tree. So let's get started. We go to UQ Blackboard, and as usual we select the practical and then go to the Jupyter Notebook. And this week we are going to study about the tree. So we have to download this file, trace.ipynb. This is Jupyter Notebook file. Just click and then you will directly download the trace.ipynb. So after that, we have to go to our zone and you will have the empty Jupyter Notebook like this, and just upload the file, trace, and then just upload. You see, now we have trace.ipynb on our Jupyter Notebook. So just open the file and we will see the content that we are going to study. This module uses the Python package called a binary tree. This can be installed by running pip install binary tree in your command prompt or Anaconda prompt. So because this Jupyter Notebook run on our zone, uh, inside of the UQ zone, not in our local machine, so we have to install this package, binary tree package, on zone. But let's try to install using the Jupyter Notebook. I'm not sure. Okay, let's see. Okay, maybe we can start to import this one. Then what's going on? I think. Okay, so inside of our zone, there is no module called binary tree, so we have to install it. Let's say if we just install here. I'm not sure. I think I'm not sure. Sorry. Let's see. Okay, no. So I think we have to go to our zone and then install this library, this package. If you're using Windows, you can download PuTTY, but if you're using Mac, you just go to the terminal. But before you log into your UQ zone, uh, we have to remember about the UQ zone practical, and then this project template and guide, and this one zone. So before we log in using SSH, we have to connect to our VPN. Okay, okay, and then go to the terminal. And so this is PuTTY. So if you're using Windows, you just need to download the PuTTY and then start to log in using SSH using PuTTY. So this is the link. Maybe we can just copy. Then let's say here. So, and this is my zone name. Okay, so this is my student ID. So put your student ID here. Add this is a zone name dot zones dot eait.uk.edu.au, and then go to the terminal SSH, this one. Okay, and then type your student password. Okay, now we are inside a UQ zone. Let's see. Let's see to install this one using pip. permission init, so I think we have to use sudo. Okay, now we can start using Python, and then from binary tree import tree. Okay, no error. It's mean we have a binary tree. So maybe we can just refresh it, and then let's see. Okay, now we can import. So we can start to study the complexity of tree. First, we have to import a tree from binary tree package. So tree BST, build, and node. And then we also need random and then time IT, because we want to uh, we want to understand the complexity, which is the time execution. So we need this package, and then of course matplotlib for plotting, and then math, and p plus. I think p plus is for, because we are going to study two types of trees. The first is binary tree, and the second one is p plus 3. Yeah, p plus 3. Okay, so I think you already got this material from your class, maybe. So this week we investigate trees and their associated insert, delete, and search function. So we are going to study about the average and then worst case implementation for binary tree, as well as the p plus tree. So yeah, as I told you before, that we need a binary tree package. The package is coming from this one. So if you want to study more, you can just open and see for more detail of this package. Okay, so let's go. This is the example how we create a node using the package of binary tree. And then this is how we generate random BST and return its truth. So for example, we define a variable my BST equal to BST height equal to 5. And then you see the height is 5, 1, 2, 3, 4, and 5. So if we just say 15. Okay, so we have to execute this one first. Okay, so no module name b plus, so I think we have to install this one. Ip install b plus. Huh? Oh, b plus 3. Okay, so we have to install b plus 3 on our zone. Okay, we need sudo. Okay, so just refresh, reload. So we need to execute this one. No module b plus. I think this is maybe b plus 3. Let's see. Okay, so this is how we create a node, and this is how we uh, create a random BST. So let's see, this is 5. Okay, because this is random, so every times you execute, it's going to change. And then how if 15? Oh, must between 0 until 9, sorry. Let's say, okay, 8. Oh, it's too big. Okay, maybe just 3. Okay, right? 7. It's too big. Okay, 5 is the best one, I think. Okay, so this is how we generate a random BST. And then, okay, binary search tree. Binary tree on average is log n, height for a random insertion of n node. So we would expect a search for of a random tree to take all log n time. But what if the tree wasn't log n height? So in the worst case, the binary tree, the complexity of binary tree, it might go to the on times, not the log n. And this is the function for search. So yeah, we are going to try the search function on binary tree. So if we read this function, let's see this one, search iterative root and then key, current node equal to root, while current node is not known. If key equal to current node dot value, return current node. So this is how we search a value on a tree, on a binary tree. Okay, so we are going to use this code below when we want to compare the complexity of the binary tree in case of the average case, the best case, and also the worst case. Okay, just let's we execute this block, and then this is for search, and this is for insert, and this is for delete. Okay, so let's see about the insert. So BST insertion begins with a search of tree to find the correct leaf location to add the new value. Once this leaf is found, we simply add the new value in this position and we are done. Based on this description, it should be clear that the insertion algorithm will perform very similarly to the search algorithm above. Yeah, so okay, let's just try. Okay, so this is okay, maybe we can just okay, so this is the function of insert. So if root is known, root equal to node, else if root dot value equal to node dot value, return this one, and then you can read carefully by yourself. And this is the example of insertion. For example, root equal to node 5. So if you want to insert, there are two parameters. The first is the root and the second is node. So insert root node and then the parameter. Okay, so this node is coming from here, coming from the binary tree. Okay, just let's see what happened. Okay, so we insert the node is root equal to node 5. So this the root is 5, and then insert root insert to this root node 4. This is 4, and then insert root node 6 and then 7. Okay, so this is how we insert a value on BST. And then how about the delete? So binary tree deletion is more complex process. There are 3 cases we must consider. The first is what if the node is leaf, and then the node has one child, and then the node has 2 children. So in the first case, we can just remove the node. So if the node is leaf, for example, if we are going to remove the 7, so we just remove it, right? Because there is no another leaf under the 7. But how if the node has one child, for example, like 6? So if we want to remove 6, so of course there will be another case. And then how if What if the node has two children, for example 5? So what if we want to remove 5? So in the first case, we can just remove the node, like as I told you before. If we are going to remove 7, we just remove 7. In the second case, we replace the node with its child. So if we going to remove 6, we replace with the 7. In the third case, we need to replace the node with the next smallest node. So the largest node in the left subtree, the predecessor node may have 0 or 1 children, so this case will fall in the first two options. And the deletion in a PST is also log n time. Try to predict what the tree will look like after each deletion, then run the code again. So this is gets the minimum node in the subtree, and this is the function for deletion. So you can read this function carefully, and then if not clear, you can just copy and then paste on another Jupyter notebook page, and then try to modify it. Okay, so this is okay. Let's see, we create this PST, and then how if we are going to delete maybe, yeah, this one, 10. So we are going to delete 10. Okay, and then let's see if we are going to delete 9. Okay, see, and then how if we are going to delete 7. Okay, so this is how the delete works. So this function is implement this tree case. So what if uh, the node is leaf, and then how if the node has one child, and then how if the node has the two children? So we can see here these three case are implemented here. Okay, so and then how about the timing investigation? So the best case, average case, and worst case. So we have said that the function of binary search tree operates in O log n time, but in the worst case, they operate in ON. So let's investigate the effect of tree balance on the running time. We will use the search function for simplicity. So in this case, we only use the search function, so no insertion and deletion. Running the code below without editing, it shows the comparison between the best and average cases. Note the relationship between the two groups, uncomment the line plotting worst case, and run the code again. Note the huge difference between O log n and ON. So here we only want to compare between the best and average. So that's why for the worst case we just we comment it, right? And then maybe next time after we run this one, we can rerun without comment the worst case. So this is similar uh, with the previous video, the complexity. So how we calculate time, like this is the start time and this is the end time, and inside and between them we have search iterative, right? So this is the search iterative function, this one. Okay, so in this case we are going to compare the worst case, best case, and then average case. The worst case function is here, the best case function is here, and then the average case is here, right? Okay, let's see. Just run it. Yeah, it takes time. I'm not sure how long it takes. Okay, so this is the result this is for the best case and average case of the BST. Okay, or if we just rerun again. Okay, this one. This is for the best case, this is for the average case, right? And then how if we just uncomment for the worst case? I'm not sure. This one. Maybe it's going to take, I don't know, but just let's see. Okay. Okay, so now we understand the comparison, right? So before, so if we comment the worst case, you see that like between the average case and the best case is not too much different, right? Here. So for example, the sample size equal to 800, we see the time is not too much different for the best case and average case. But if we uncomment for the worst case and then see what happened, oh, too much different, right? So this is the worst case of BST, and this is the average and the best case of the BST. This code block is for finding the depth of the different trees. So we have a function get best here, get average, get worst, and get depth. So inside of this get depth function, we have a variable base, which is equal to get base, and then variable average equal to get average, and then variable worst it's referred to the get worst. And then how if we just call the get depth 100, we see that the worst case is 100, of course, the best case is 6, the average case is 11. How about the 1000? Worst case is 1000, sure. Best case is 9, and then average case is 20. And then 10,000. Okay, so now we are going to study B plus. So there are two main difference between B plus and binary search tree, BST. It's not has maximum number of children greater than 2. The insert and deletion algorithm must ensure the tree satisfy a balancing property. It's not must be between half full and full at all times. Okay, let's see. This is the library background. We will use a full P plus 3 implementation. The tree is initiated as a P plus 3 of order n. Okay, so as I expected, I think we use wrong library. So it's not P plus 3, but it should be P plus. But I don't know where the P plus coming from. If we looking at P plus Python, yeah, this is the P plus 3, not P plus. So I suspect maybe we can find, so there is no another attached file here, right? So maybe under the learning resource, and maybe on trace material, maybe there is another file there. Okay. This one, binary trees notebook. I think maybe inside of this notebook I just extract. Okay, this is the binary tree notebook. Okay, so this one pi plus, so we have to import this one. So import that one. So how to import it? As usual, upload p plus, this one, open, and then upload, and then let's see, import p plus, import all. Okay, yeah, so maybe okay, let's see, this code is from Python true, yeah, I suspect. But let's see, we just import uh, p plus Python 3, p plus Python 3. and then upload p plus Python 3. Let's see. I'm still not sure. Okay, it's worked. And then go to the p plus here. Okay, it seems working, but not sure here. So this one, we are going to compare between the worst case binary tree, the average case binary tree, and then the average case of p plus, and then the worst case of p plus, right? So four algorithm that we are going to compare. Okay, so let's just run it. Okay, so we got an error here. Generator object has no attribute next. Okay, I'm not sure. Okay, let's see. And then what is the line? 430. 430, this one. Okay. Yeah, I think, okay, how if we just copy and paste the error? Okay, so I suspect this code is still under the Python version 2 because yeah, so the problem is when we write a code under the Python 2 and then we run it on the Python 3, so it's going to we will have a trouble because there are a lot of syntax that it's really different between the Python 2 and Python 3. So yeah, and it seems we need a lot of times to change everything from the Python 2 to okay, this one next iterator method. So Python 2 is using iterator.next, but for the Python 3 is using the different syntax, right? Okay, so I think we just skip for this one, but at least we can understand the result. So okay, maybe I just need to delete this one and then upload 3 and then see the result directly. Okay, so here, so if we want to compare between b plus and binary tree, we can see here. So the green one is the average case of binary tree, the red one is the worst case of binary tree, and then the blue and orange is the average and worst case of p plus. So it seems that p plus for the average and worst case they have like a small difference. And then how about this one? This is, so if this one is about search, this is the search function, and how about the insert? So in terms of insert, we compare the worst case of the binary tree, average case of binary tree, and then the worst p plus, and then the average p plus for the insert. So we have this tree here, average case p plus, worst case p plus, and then average case binary tree. So the green one is the average case of binary tree, and then the blue and orange is the average and the worst case of p plus. I think that's all for the video lab practical today. So I hope it can help you. Okay, see you next